Hello everyone and welcome back to another video here of the Hidden Quantum Champions at the Polaris School of Quantum YouTube channel. In today's video we are going to look at a company that from my point of view was a very hidden champion until very recently when it got discovered by Google's quantum AI team and actually became part of it. And maybe you've already seen in the title which one I'm talking about, or you already know it from this introduction. But with that, let's jump right into the website. So today we are going to look at Atlantic Quantum. So here it also says, like the quick warning ahead for all of the Hidden Champions fans, Atlantic Quantum is now part of Google Quantum AI. Click below for our official statement. To stay connected, follow our progress at quantumai.google, I guess .com or .something. We will not do that now. We just look at the website as is. But yeah, just for you to know, with that, I mean, they are not, let's say, an own entity anymore. They're part of Google's quantum AI, but I think it's still very interesting to see what they're actually doing and what is the relation and what they're working on. So with that, let's jump right into what we see here. So it says the first quantum integrated circuit tackling the three biggest challenges in quantum computing with a single processor, so speed, accuracy, and scalability. And here we see the processor that they're talking about. Now, their approach, our approach, a new Moore's law for quantum compute. Integrated circuits unshared in a new age of classical computing by unlocking ensured a new age of classical computing by unlocking scalability. Before integrated circuits, transistors were already more compact and less prone to error than vacuum tubes, but the industry couldn't scale until the integrated circuit kicked off Moore's law. Atlantic Quantum is doing the same for quantum compute and accelerating scalability. We are integrating our qubits and cryogenic controls into one modular chip stack to create the first integrated circuit for quantum compute. This is the key of achieving real-world quantum advantage at scale. Now, one step back. I guess a lot of you know what Moore's law is about, but just as a quick side note here. So Moore is the, I think, former CEO of Intel, who basically predicted that, okay, with every X amount of years, the device size will halven, or in other words, the number of devices on a chip will double. So that means basically for a long period of time. And now we are reaching, I think, kind of the end of that transition. But for a long period of time, the number of transistors that you could put on a wafer, on the standard size wafer, and therefore also into the chips that go into your computer, your smartphone, whatever, the size of the elements on top of those, they've been halvening or shrinking exponentially, because if you always put something in half, you actually exponentially reduce the size of that object. And that actually means the number of transistors on your chip has doubled every year. And therefore, our computers have increased basically by a factor of 2 in calculation power since the beginning of this trajectory. And of course, that means we have an exponential growth. That means an explosion in compute power. And that's what is enabling all of these different things that we are seeing today, where like your smartphone is more powerful than the supercomputer that sent people to the moon for the first time. And now basically when looking at quantum technology, people are trying to draw, let's say, comparisons here and saying, okay, now we have 1 qubit, then at some point we have 2, maybe we have 4, 8, and so on, all the way up to X amount of qubits. And at some point, this will become, let's say, a relevant number so that you can do actual calculations with that. Now, there is a bit of a debate on whether this is a fair comparison, because technically, let's say, using all of the technologies that we have today that we are using to create those chips, we could actually print quite a lot of these circuits onto the chip. But there's other challenges that come along with it, like, for example, in the solid state systems, cooling those units down. So if the chip gets larger, you have more control lines that are going down onto your chip, that are running all of these control signals. All of this has to be cooled down, and the cooling power becomes a limitation quickly. There are other people that are saying, okay, but you have to be able to coherently connect all of these qubits. So you have to, in order to really make use of your quantum system, you have to create a superposition state where there's a superposition over the whole system. So quantum information is distributed over all qubits. And this can only be achieved running a couple of gates in a row, and the error rate of these qubits is way too high, so this is not possible. That's where the error correction comes from. And then in the other direction, there are now different approaches of how to actually solve this cooling problem. And I guess here we have one of those, because here we see we have the qubits, we have the controller unit sitting together with the qubits in this environment, and then there's only an input-output part which goes up. So I guess the idea is to move more of the electronics closer to the qubits, or more of the intelligence closer to the qubits, so that you have less of these control lines which have to be cooled down. There's also other approaches saying, for example, that you just need to make the cryostat bigger. I think IBM was working once, and I'm not sure if that's still something they're investigating, but they were blowing up the size of the cryostat so that you could put more of these lines also into the system. Okay, then there are some benchmarks here. So it says fastest clock speeds, superconducting circuits, including our fluxonium-based architecture, deliver fast clock speeds. This is critical for running utility scale applications. Then lowest error rates, that's what we just talked about, right? Our superconducting fluxonium-based qubit architecture has a significantly lower operating frequency than other qubit modalities. We leverage this to achieve record low error rates. And then also, lastly, most scalable architecture. This lower frequency allows us to collocate control electronics with the qubit chip, unlocking a new scaling trajectory and dramatically reducing both system cost and cost per qubit. And then here we see one of these superconducting qubit systems. Well, actually, mainly we see the cryostat. So you see, these are all the control lines here. So they look like this. These are radio frequency guides, more or less. So they're guiding the signal down there. They are electric lines, coaxial type of lines. They're very stiff. So they are like stainless steel tubes, more or less. And they are moving a signal all the way down to the lowest cryogenic stage. So you have different stages here. You see these plates. They have different temperatures to them, associated to them, and the signal goes all the way from room temperature, which is up here at the roof, all the way down to these millikelvin, so minus 273 Celsius, more or less, signal lines. Now, very quickly, let's see, there are some publications also down here. You see 2023, 2024, and then there's a news part here as well. And you can actually follow the news here. So it says fast control methods enable record setting fidelity in superconducting qubit all the way up to October 2025. I'm recording this in November now, where it says Atlantic Quantum is now part of Google Quantum AI. And then, as per usual, there's an investors part down here. There's a follow us down here with linking to all of the different social media, and it also says Cambridge, USA, Göteborg, Sweden as the locations, I guess, of the company. Now, quickly scrolling up and looking at Our Advantage tab, it says a single processor designed to deliver unparalleled utility scale, speed, fidelity, and cost. Here you see somebody holding the sensor with a tweezer with a glove on. I guess this is like in a clean room setup. We see the benchmark that we've seen before, and then there's some information down here which says competing options all comprise on at least one of these three benchmarks, and then we see the benchmarks down here. So we have problem. Quantum computing platforms are varied making comparisons difficult. However, all platforms are judged on 3 universal benchmarks: clock speed, fidelity, so error rates, and stability. Current industry leaders excel in 1 or 2 benchmarks, but have yet to achieve all 3. Some challenges can be addressed through engineering, while others stem from fundamental physics, requiring entire new breakthroughs. Solution: our fluxonium-based superconducting qubit architecture allows us to excel in all 3 benchmarks. And fluxonium is, let's say, one specific type of a superconducting qubit architecture, like how it is actually designed. There are also transmons and other types of names for these specific qubits. It has to do something with the capacitive part versus the flux part of the architectural design of the qubit. And I mean, if you want to know more about that, let me know down in the comments below, then I will make a video specifically on superconducting qubit architectures. But let's go back to the text. So it says, its fast clock speeds match other superconducting systems, while its low frequency qubit state shield against noise for record low error rates. Most critically, it enables the world's first quantum integrated circuit, combining controls and qubits into a single modular chip stack inside a cryostat. This breakthrough reduces complexity and cost, unlocking scalability and paving the way for utility-scale quantum computing. And here we now see this triangle between fidelity, speed, and scalability. I guess these are some of the competitive architectures that are mapped down here, and you see none of them is covering everything, but their solution is actually excellent in all of these 3 areas. And I guess if you want to see what excellent means to them, you have to check out the publications that they have linked down here about measuring these different aspects of the system. Now let's quickly also check out the About Us tab. So it says, born from MIT and Chalmers University, we are a team of experts dedicated to building useful quantum computers. Quantum computing will change the world, enabling a step change that will transform whole industries once talented people find ways to make them work. Our team is singularly focused on turning scientific and engineering rigor into practical solutions. And it's why we continue to hire the brightest minds across oceans. Across oceans because they are spread between those 2 different locations. Then I guess here we see the team, which is moving with this quantum wave across the screen. Here we have the leadership team, as well as, let's see, the different heads of the different areas. And then again, there's this link to the publications down here. With that, here's also some list of investors, maybe worth to mention. So Engine Ventures, United States Innovation Technology, US IT, Glasswing Ventures, E14 Fund, Future Labs Capital, Neotribe Ventures, Mass Ventures, Blindspot Ventures, and Chalmers Ventures. And I guess since they have now become part of Google, Google is probably the only investor now. They've probably bought out all the other ones. With that, I think we are already at the end of today's video. If you like the video, please make sure to actually share it and give it a like. Share it with your friends. If you don't want to miss out on the next one, then please make sure to subscribe to this channel. And as always, please make sure to stay hydrated and see you in the next one. Bye bye.